So welcome to Everyday Mathematics. Today we're still on the 2024 Caltech Math Meet set of problems, and we are on the finals, problem number 30. The problem was the definite integral from x equals to 0 to x equals to 1 of x times the natural logarithm of x over 1 minus x squared. So this problem exploits geometric series or geometric progressions, and we'll see how we'll be able to exploit that to really be able to solve this problem. I've seen folks that have used Taylor's expansion of the natural logarithm. I think that's a little bit too much, but let's move ahead and see how we may be able to solve this problem. So as I mentioned earlier, looking at 1 over 1 minus x squared as a geometric progression, starting from k equals to 0 to k tending to infinity, we can re-express that part as this series as shown here. So that the first term is 1, x to the power 0 is x to the power 2 times 0 is 1, and then we have the common ratio being x squared, and that's what we've done here. So the next thing we'd want to do is we'd allow this x to percolate through into the summation part here. So now we have x to the power 2k plus 1. We can also allow the logarithm function to cross into the summation sign. Now here, the important thing to know is that if you are integrating a sum of terms, that's the same as summing the integration of the respective terms. So we can interchange the integration and summation sign without losing anything. So now here we have a summation from k equals to 0 to k tending to infinity of the integral from x equals to 0 to x equals to 1 of x to the power 2k plus 1 times the natural logarithm of x. I would like to use integration by parts here, where we say, okay, so if you have a product of a function v and the function, the derivative of function u, then when you integrate that, you have the product of u and v minus the integral of the product of u and the derivative of v. So we choose the natural logarithm here to be v so that we can express x to the power 2k plus 1 as a derivative of a certain function, and that is the derivative of the function 1 over 2k plus 2 times x to the power 2k plus 2. So now we can go ahead and use integration by parts to solve this problem. So the next thing is, the product uv is going to be x to the power 2k plus 2 over 2k plus 2 times the natural logarithm of x, minus, we can pull the constant out, 1 over 2k plus 2 times the integral from x equals 0 to x equals to 1 of the derivative of the natural logarithm of x, that's the derivative of v, times u, which is x to the power 2k plus 2. Obviously, this constant here was just pulled out for convenience sake. And so limit as x tends to 1 of this function, the natural logarithm of 1 is 0, so this entire thing goes to 0, minus limit as x tends to 0, x to the power 2k plus 2 will be 0 in that instant, and this also goes to 0. So this entire part goes to 0. And what we're left to now is the derivative of the integral of the derivative of natural logarithm of x, which is 1 over x times x to the power 2k plus 2 times the negative 1 over 2k plus 2. So what that means now is our problem now has reduced to the summation from k equals to 0 to k tending to infinity of the negative of 1 over 2k plus 2 times the integral from x equals 0 to x equals to 1 of x to the power 2k plus 1. Integrating that results into x to the power 2k plus 2 over 2k plus 2. Limit as x tending to 1 of this will go to 1 over 2k plus 2. When x tends to 0, this will go to 0. So ending this now results into a problem that is a summation from k equals to 0 to k tending to infinity of the product of negative 1 over 2k plus 2 and 2k plus 2. So the question now that we have is, what do we get when we sum negative 2k plus 2 squared from k equals to 0 to infinity? Right? Let's just pull the negative sign out. What is the summation from k equals 0 to infinity of 1 over 2k plus 2 squared? This is interesting. Now, we can borrow from the Basel problem, but before we do that, let's just see what that looks like. The summation, when k equals to 0, that's the same as 2k. In the denominator, we have 2 times 0 plus 2, which is 2 squared. So this is the same as 1 plus 2 squared. When k equals to 1, it's 2 times 1 plus 2, which is 4. So 1 plus 4 squared. 1 over 4 squared. When k equals to 2, that's 2 times 2, which is 4 plus 2 is 6. So 1 over 6 squared, and so on and so on. So we see that we are looking at the even terms of the Basel problem. The Basel problem states that when you are summing from k equals to 1 to infinity of 1 over k squared, that adds up to pi squared over 6. If you don't know much about this, I invite you to go ahead and search for what the Basel problem is. And there's a lot of material that can show how you're able to derive the pi squared over 6 as resulting from the summation of 1 over k squared. Anyway, with that in mind, we do have this negative of open bracket 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared, and so on. Let's pull 1 over 2 squared out. And so inside the bracket, we're left with 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on and so on and so on. So we clearly see that inside the bracket, we do have the Basel problem summation. So we can just go ahead and plug in the pi squared over 6 in place of whatever is in the bracket. And so we have negative 1 over 2 squared times pi squared over 6. 1 over 2 squared is a quarter. So negative a quarter times pi squared over 6 becomes negative pi squared over 24. And this is the answer that was expected. Anyway, so that's the short of it. Thank you so much for those of you who have tuned in this time around. If you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. And if you do like what we're doing here, please don't hesitate to like our video. If you have somebody you think might benefit from what we're doing here, please share the video with them. It's been an absolute pleasure. Until next time, have a blessed time ahead. Thank you.